Hi, everyone, and thank you for joining today's virtual meetup and talk. And the title is Advanced Data Modeling, NoSQL Database. My name is Shtub, and I'm head of training at ScyllaDB. The topics that I will cover today are, I'll start with an introduction, and then depending on the participants, depending on you, I would like to go over some basic architecture and data modeling concepts just to make sure we're on the same page. So unless you tell me that you already know it, we're going to go through it. Then I'll talk about more advanced topics like choosing a partition key, collections, counters, user-defined types, and TTL, or time to live, large partitions and collections, hot partitions, cardinality, and tombstones, and some common mistakes, diagnostics, and prevention. So like I said, this is me. I'm head of training at ScyllaDB, and I lead the training here at the company. My background is as a software engineer, and I am based in Israel. Everything that I will be discussing today, almost everything is relevant for a few NoSQL databases. I will use ScyllaDB as the database as an example, but the concepts that I will be covering are relevant for other databases, namely for Apache Cassandra, which is a database that's compatible with ScyllaDB, and for Amazon DynamoDB, as well as others. So I will try to point out differences when I see them. And I would also like to make this talk as interactive as possible. So I have another screen with a chat window open. Feel free to ask questions. Tell me if I'm going too fast or too slow, or any other comments that you have. Before I get started, two very useful resources. So most of the topics that I will be talking about today are covered in ScyllaDB University. ScyllaDB University is our online learning and training center. It's completely free. It's online, and to get started, you just log in, you create a user, and you can take different courses and different lessons. They come in forms of videos, slides, hands-on labs, and so on. So feel free to check that out. Again, you can dig into the different topics that I will be discussing today in Scylla University. Another useful resource is our documentation, docs.scylladb.com, and there you have procedures and more in-depth material. So let me start with a few words about ScyllaDB, which, like I said, is a NoSQL database that I'm going to be using as an example when I explain the different topics today. ScyllaDB is a software company and also a name of a NoSQL database. It's open source, it's community-based, and it's used by some companies that you are probably familiar with. And we have a few flavors of the software. One is open source, where you can access the code, play around with it, add your own features, and just run it. Another is our enterprise version, where you get some features that are not available in the open source version, as well as our support. And the third option is our database as a service offering called ScyllaDB Cloud, where basically we manage the database for you. We take care of things like upgrades, security, backup and repairs, and you can just focus on your core business, which is probably not administrating a database. Some of the attributes of ScyllaDB: high availability, and that means that the system remains available even if some nodes go down. The system is highly scalable, meaning that it can run on multiple data centers and on multiple nodes spread around the world. The system is very performant. I'll show an example in just a bit, but we're talking about single millisecond operations per second. We're talking about millions of operations per second. So if you require high performance, you can consider ScyllaDB. Low maintenance. So I'm assuming some of you are familiar with Apache Cassandra, and many users that are familiar with Apache Cassandra know about tuning garbage collection and all sorts of problems that come with that. So ScyllaDB is written in C++, and therefore it's easier to maintain. Not just that, but that's one of the reasons that make it easier to maintain. And like I said, it's a drop-in replacement for Apache Cassandra and DynamoDB. If you're running one of those databases, you can simply change the underlying database to ScyllaDB and run your application as it is. I have some benchmarks here. I don't really want to go into the details. They're available on our website, but just to give you an idea, I'll compare a use case where one of our users switched from Apache Cassandra to ScyllaDB. In Apache Cassandra, they were running 40 nodes. They switched to 4 Scylla nodes, and they got a result which was 2.5 times cheaper, and they got much better performance, so 11 times better latency. So that's just an idea, and it makes a lot of sense to make the migration. And again, you can look at specific migration use cases on our website. I mentioned performance, so here I have a link. And by the way, I didn't mention it, but we're going to be sharing the slides with you, including those links. So you don't have to worry about writing things down or, I don't know, taking photos of the slides. We'll share them with you. Yeah, afterwards in an email. So here you have an example where using this repository, using this example, you can run 1 million ops per second demo with ScyllaDB, very straightforward, just by running a few commands, and then you can see what happens. So that's just a hands-on demo where you can see how ScyllaDB works. Now, the topics that I want to talk about today are relatively advanced, but to talk about them, we need to make sure we have some kind of basic understanding of more basic concepts. So if you can write in the chat window, if you know about things like, or let's do this, if you don't know what a node ring or data replication, consistency level, what those concepts are, please write so in the chat window. So just so I know how fast to go through this part. So basic data modeling and architecture. Okay, so I see some people don't know. I'll start with the basics before I move on to more advanced topics. Okay, thank you for answering. So I mentioned that ScyllaDB is a distributed database. And again, I'm using ScyllaDB, but this is relevant for Apache Cassandra and DynamoDB. And that means that the database runs on multiple nodes. And when I say a node, what I mean is the database software running on a single server on a machine. So it's a distributed database, meaning that the same database runs on multiple nodes. And these nodes work together to provide service to the user. Okay, a cluster is a collection of nodes. And in production, each cluster has between 3 nodes, which is considered the minimum number of nodes to run in production. And this can go all the way to hundreds of nodes, okay? So a single cluster, single ScyllaDB database application can run with a few hundred nodes, okay? That's important to understand. Another important concept to understand is that in ScyllaDB, Apache Cassandra, DynamoDB, data is replicated. Now, what does that mean? That means that for each piece of data that the database holds, we hold multiple copies of that data. And those copies are stored on different nodes. If you remember at the very beginning of my talk, I mentioned different attributes of the database. And the first one was high availability. High availability means that even if a node goes down, or even an entire data center goes down, the system is built in such a way that it would still be able to serve requests. Okay, so it's very highly available, and that means that there is redundancy built into the system. And the replication factor determines the number of nodes where data are replicated. Okay, this is something that can be defined by the user, and it's done automatically by the database. So once you, as the user, define your replication factor, data is automatically replicated across different nodes, and you don't have to worry about that. However, it is important to understand that this is something that is happening under the hood. How do we define it? So there is a concept called key space. A key space in ScyllaDB is basically a container of tables, okay? And when we define a key space, as we can see here in this slide, we can see that, among other things, we define the replication factor. So in this case, the replication factor is defined as 3. And that means that for each row in my database, we're going to replicate that row 3 times to 3 different nodes. Okay. And then for each table within this key space, it's going to inherit this replication factor setting. Now, of course, there's a trade-off here. Like in many other things in life, we have trade-offs. So if we define a higher replication factor, we're going to have higher availability, meaning that even if some nodes go down and become unavailable, we're still going to be able to serve requests. However, there is a cost to that, which is we require more nodes, and the cost might be higher because it requires more hardware. And there also might be performance implications as we're writing more data to more nodes, and that means that this would impact performance. I mentioned high availability. A few other important concepts with that regard. So in ScyllaDB, we don't have the concept of leader-follower nodes or master-slave or any other name you want to call it. All nodes are created equal. All nodes can serve requests. And again, that goes together with high availability. Even if some nodes go down, we don't have a single point of failure. So let's look at an example. What happens when we have a replication factor of 3? So in this example, we have a 5-node cluster. So we have 5 different machines that are working together to serve requests. And here, the user defined the replication factor to be 3. And that means that when we write a piece of data, say we write this green cube, whatever it may be, it's going to be written on 3 different nodes. In this case, node 1, 2, and 3. We write another piece of data, and that's also replicated to 3 different nodes, and so on. Okay? That means that each node holds a part of the database, of the data, and that data is replicated across different nodes. Screen share has stopped. So if you can write in the chat window if you can see my screen or not. You can see it. Okay, so maybe it's just for one user. If you have a problem, do let me know. Thanks. So there's a question regarding load balancing. It's not exactly load balancing because here we're not really, well, there is load balancing, but that's a separate concept. Here we're replicating data, and that goes together with high availability. The way that this works under the hood, and this is also important to understand for the next topics that I'm going to talk about, is as follows. So we have here our 5-node cluster, just like we saw before. And in ScyllaDB and Apache Cassandra again, when we define a table, here we have a table with 3 columns, pet chip ID, a time, and a heart rate. Okay, so when we define a table, we need to define a partition key. A partition key can be 1 or more columns that are part of the table. And it's very important how we choose our partition key. Now, what happens under the hood when we write data? So when we write data, say we write this first row with a heart rate 120, what happens under the hood is that the database looks at this row, it looks at the partition key, it performs a consistent hash function, also called the partitioner, and according to the hash result, it knows which nodes are responsible for this specific row. Okay, so each one of the nodes has a token range that they're responsible for, and by using this algorithm, the database knows which node or nodes would be responsible for each piece of data. Now, from this, you can understand that the way we choose the partition key is quite important. Another way to look at it is, I mentioned the key space, which has multiple tables. The key space has settings like the replication factor. Each table also has settings, things like the primary key. The primary key is composed of the partition key, which I just talked about, okay? Pet chip ID, in our case, is defined as the partition key. And we can also define a clustering key. A clustering key determines how data is ordered within that single partition. Okay, so for example, we can define the partition key, going back to my example, to be the pet chip ID. And then we can order the data within that specific partition. So for a given pet chip ID in our case, we can order the data according to the time. So in that case, we would define the time as the clustering key. Okay, so we would have, if I go here, we would have a partition key. And within that partition key, we would have different times. And for each time, we would have the heart rate. Okay, so this is how data is ordered within the database. And again, this is happening under the hood, but it's important for you to understand in terms of data modeling. Okay, so there is a question, and the question is, how does the system manage concurrent requests for changes if there's no master and slave? So that's a good question, and it's a complicated question. I didn't talk about the CAP theorem, but the CAP theorem states that in distributed databases, we try to achieve 3 different attributes, and they are availability, consistency, and partition tolerance, and that there's always a trade-off between those 3. We can't really achieve all 3 of them. We have to give priority to 2 out of those 3. And the way that ScyllaDB and Cassandra work is that they use, we can have concurrent writes because we don't have a master and a slave. Typically, we use the clock or the time to determine which is the latest value. And we have something called eventual consistency, which brings me to the next slide. And just like the availability is or can be defined by the user with a replication factor, we can also determine the consistency level that we require according to our application, according to our specific use case. So that goes together with the concept of consistency level. And consistency level is the number of nodes that must acknowledge a read or a write request. Some examples are one or quorum, like somebody wrote in the chat window, local quorum, and all. And the consistency can be defined per operation, okay? And that means that we can have different queries with different consistency levels, again, according to our data model, according to our application. Let me give you an example. So say we're, in this example, we're doing, we have an IoT use case, and we have a collar that's on our pet, say our dog, and that collar is sending every second the heart rate of the dog to the database. Okay, so in that case, if it's writing every second, maybe we don't require a very high consistency level, because even if we miss 1 second or a few seconds, it's not the end of the world. So in that case, we can use a lower consistency level. However, maybe we have an application that has to do with financials, and we're looking at bank accounts or something where we require a very high consistency, and we can't make a mistake, and then we would use a higher consistency level. So let me maybe also show it on this slide. So if we look at this example, and we have a replication factor of 3, so let's look at the green cube. Let me go back here. So right now we look at this piece of data and it's replicated across 3 nodes. If we would now perform a read request and we would define the consistency level to be quorum, then that would mean that a quorum of those 3 replicas must respond or acknowledge the query in order for it to be successful. So a quorum, since we have a replication factor of 3, would be 2 out of those 3 replicas. And that means that even if node 3 goes down, say there's an earthquake, a fire, a network failure, whatever there is, node 3 is destroyed, then we can still perform the query because 2 out of those 3 nodes are going to respond to our request. In the exact same scenario, if our consistency level would be defined as all, then all 3 nodes would have to respond. And if one node would be down, then the query would be unsuccessful. Okay, so that's just an example. Of course, there are many different options, and it really depends on your use case. Okay, moving forward, multiple data centers. So ScyllaDB is built to work with multiple nodes, and it's also topology aware. And what that means is that the database knows about the topology of the network, and we can define different data centers to work together. Okay, so in this example, we have 5 nodes in the US data center, we have 3 nodes in the EU data center, and 5 nodes in some data center in Asia. And this makes sense for a few reasons. Maybe the first one is, again, high availability. So if a rack within a data center, for example, an availability zone, or even an entire data center, that's very unlikely, but that might happen. If an entire data center goes down, say the US data center fails, we could still serve requests from the 2 other data centers. And once the US data center comes back up, it would get updated by the other data centers streaming the data to the data center that was down. And by doing that, we would maintain our high availability. Another reason is for performance. Again, some of our users and customers have very high performance requirements, and it would make more sense to serve a user, say, in the US from the US data center and not from one that is geographically further away, which would translate to more latency just because of physics and because of the geography. And maybe a third reason would be for compliance reasons. So maybe there are some rules in a specific geographical location, say in the EU, where data about the users in, say, the EU cannot leave that geographical area. And we would keep all that data within the EU data center. Okay, so that's about multiple data centers. Again, with data centers, all data centers are created equal. We don't have the concept of leader follower or anything like that. Okay, moving forward. How do we choose a partition key? So I mentioned a partition key determines how data is partitioned across the different nodes, as well as the clustering key. So there are some differences between data modeling, between NoSQL databases and relational databases. We have a course on that on ScyllaDB University. I won't go to the very, very basics because I want to cover some more advanced topics. But maybe the most important thing is that when you're creating a data model for relational databases, typically we start by thinking about the data, and then we create the entities and the relationships between them. And only at the very end do we look at the different queries that we have in our application. When we do NoSQL data modeling, it's not exactly the same. So we think about the data and the entities and the relationships, but also at the very start, we have to think about the queries that we're going to perform. And we create the data model according to the queries that we know we're going to perform. Okay, so some things that can go wrong are things like hotspots, imbalances, large partitions, and tombstones. And I will talk a bit more about each one of those things. Okay, so some best practices: follow a query-driven design approach. That's what I just said. It's very important to choose your primary key correctly. A primary key is the partition key together with the clustering key. Okay, so maybe a few rules about that. Like I said, the partition key is one or more columns that are part of the table. Each table needs to have a partition key, and for each given query, we must provide the partition key. Okay, and we must provide all of it. So if we define a partition key that has 3 columns, then for every query, we're going to be having to provide those 3 columns, because that is the only way that the database knows how to access the data. If you try to perform a query and you don't provide the partition key, then you're going to get a warning. The database is going to warn you and tell you that you can't perform this query unless you use something called allow filtering. Now, what allow filtering does is basically it does a full table scan of all your data. And the warning is there just so you know that this query is highly inefficient and we can't predict the performance results. Okay, so if you find in your application that you're using allow filtering often, that may be a sign that your data model is somewhat off and that you should reconsider your primary key selection. So I mentioned the partition key. There is also the clustering key. And like I said, the clustering key can be 0 or more columns, so it doesn't have to be defined. And also, when you perform a query, you don't need to necessarily use the clustering key. So you can provide it, but you don't have to. However, if you do provide it, it has to be in the same order as it was defined. Okay, there is a really nice lab on ScyllaDB University where you can see this in practice. It's called, I think, Basic Data Modeling Lab. And you can actually run the lab and see what happens with different partition keys, with different clustering keys. And personally, I think that's the best way to learn, by getting your hands dirty and running some code. More things to consider: even data distribution. Okay, so I mentioned there are multiple nodes, and we want to avoid a situation where some nodes hold more data than others. Okay, now, of course, it can't be completely distributed evenly, but the choices we make when we create a data model have strong impact on the data distribution. So let me give you an example. I mentioned that the database partitions the data to the different nodes according to the partition key. And for that reason, we want to choose partition keys that have high cardinality. So in the example I just showed you, we use something like an ID, and that's usually a random number that provides high cardinality. A counter example, something you don't want to do, is choose, for example, a state in the United States. Let's say we're looking at people in the United States, and one of the columns is the state the person is from. So if we choose state as the partition key, that's probably not a great partition key, because there are some big states like, I don't know, California or Texas with many people, and there are some very small states with just a few 100,000 people. Okay, so if we do that, we're going to get data distribution that's not even, and we're going to have high load on some of the nodes. I saw a question. So there was the question, what's the difference between the primary key and the partition key? So the primary key is both, wait, let me make sure I'm not giving you a wrong answer. So if I recall correctly, it's the same thing. The primary key and the partition key are the same thing. There's another name, I think it's called compound key, which is both the partition key and the clustering key. I'm 90% sure of my answer, so don't take my word for it. It's a bit complicated because ScyllaDB and Cassandra use the same terms, but then DynamoDB has different terms. Instead of clustering key, they use the term sorting key, which actually makes more sense in my opinion. But then there are different terms for the same thing, so just make sure you check that out. A few more questions. Is it best practice to include both keys? So I wouldn't say it's best practice. It really depends on your use case and on what you're doing. So in some use cases, it's not necessary to use the clustering key, while in others it is. So let me give you an example. Let's say we have a data model and we have an application like I showed you before. I mentioned we have dogs. Each dog has a collar. The collar measures the heart rate of the dog and sends the heart rate to the database. If our queries, we know in advance that they're just going to be according to the ID of the dog, then we can just use the partition key as the dog ID, the unique ID. However, if we know that we're going to have queries that are also based on the time, say we want to have for a specific dog, so we provide the pet chip ID, the dog ID, but we also want to know what was the heart rate between 10 in the morning and 7 p.m. in the evening. Okay, then we would also use the clustering key. So the answer is that it really depends. And that would probably be the answer for most data modeling questions. It depends on your use case. So partition keys can be multiple columns, but they have to be one or more columns. So yeah, a compound key is a primary key plus a clustering key or a sorting key. But let me move on, and I'll also try to leave some more time at the end for more questions. And I'll also try to answer the question about uniqueness of the partition key. Okay, so I don't want to skip this. I talked about even data distribution, but another important concept is how we access the data. So it's not just how we distribute the data. I mentioned people from different states, but it's also how we access that data. So let's say, for example, that I have people from all over the US in my database. However, the queries that I'm performing in my database are mostly about people in Delaware. Okay, so then I would know that people with that given partition key, if I choose the state to be the partition key, would have more access than other states. Okay, so that's also something I have to take into account. A really, really important concept or thing that I recommend is to install our monitoring stack. So we have a monitoring stack. It's based on Grafana. And with it, you can see exactly what's happening in the database. What are the latencies? What are the requests? You can have views that are per node, per shard, and so on. So it's almost impossible to understand what's going on in the database without installing the monitoring. Whenever we have a user asking us questions, the first thing we ask is, do you have the monitoring installed? And we ask to see some data from the monitoring stack. There is a lesson on ScyllaDB University about the monitoring stack. You can see how to install it. It's quite straightforward, but I recommend you check that out. Okay, a few more advanced topics. I won't go into a lot of detail, but just so you know about the concept, and if you want to use it, you can then know that it exists and read more about it. So we support a few types of collections in ScyllaDB, and these are sets, lists, maps, and UDTs, or user-defined types. There's a question about the monitoring tools, if they can be installed across all databases or only one database. So the tool that I showed monitors the ScyllaDB database, but it monitors the entire cluster. So if you're running a cluster with 120 nodes, then you need to install a single instance of the monitoring stack, and that will monitor the entire cluster, and you would be able to know what's going on in your entire cluster. And if you're using ScyllaDB Cloud, which is our database as a service offering, you don't even have to install it. It comes pre-installed with a monitoring stack, and you can see what's going on in your cluster. So collections. Collections are used to describe a group of items connected to a single column, and they can simplify data modeling. A good idea or best practice is to make sure the collections are small, because they can easily grow and increase latency and harm performance. This is an example of a more advanced table. We can see that we have more columns here, and here we define a set of attributes, a list of barks, and a map of positions. Okay, and let's dig a bit deeper. So sets are ordered by the natural order of the data type. So it can be alphabetically or numerically. Here we're using a set of texts. So if we add to the attributes, to the set, we add the data C. So we can see that we insert data into our table using the partition key petchip ID, and we add the attributes. We can see that it's added. And if we add more data, then regardless of how we add it, then in the database, it will be stored in alphabetical order. Okay, so that might make sense for your use case. As opposed to that, lists are ordered according to the user selected order. So it depends on how you insert the data. Okay, so what happened here? So if we have a bark with lists, and we add, say, woof, and then we add whiff and waff to those barks, and then we add to the barks meow. So this is the order that we would have. It's exactly according to the order that we entered the data. Okay, they're not reordered as we saw before with the set. Now, I've been talking for quite a while, so just to make sure you're with me, let's do a quick poll question. If you can answer in the chat window, what's your NoSQL status? The options are I'm completely new to NoSQL. That's one option. And the second option is I'm already using a NoSQL database. So if you can take just 30 seconds to make sure I'm not talking to myself. Do you have experience with NoSQL databases, or are you new? Okay, interesting. I see quite a lot of answers, and quite a lot of people are completely new. Okay, that's good to know. Maybe I'll do another talk in a few weeks where I cover some more basic concepts as well, because here it's a bit more advanced. So thank you for that. I also see that some people have previous experience with Dynamo, Mongo, Cassandra, and others. Cool. So I talked about lists. Another collection type is maps, where you basically have key value pairs, and that makes sense. Let's look at an example. Say we want to look at a position where we have a latitude and a longitude, maybe also altitude. So we can define that as maps, and that might make sense. And here we can see an example of how this is done. And again, defining the table with the position and having the position have these three key value pairs would make it easier to access than if we do it in other ways, which is also possible. Okay, another concept related to ScyllaDB, as well as Cassandra, DynamoDB, and others, is counters. Counters are a conflict-free replicated data type. They're a special type of column that is defined. And with counters, basically, we're guaranteed that updates to the counter are going to be atomic. So if you remember, I previously talked about eventual consistency and about how data is written. And I didn't really go into that, but in ScyllaDB and Cassandra, we know that the data is going to be consistent, but we don't have necessarily atomic or highly consistent transactions. And with counters, we know that the operation is going to be atomic. Okay, so it's not eventually consistent, it's conflict-free. And the operations that are supported for counters are increment and decrement. There are a few rules for how to use the counters. They must, all the other columns must be part of the primary key, and the counter columns cannot be part of the primary key. And here you have an example. And again, you can see a hands-on example on ScyllaDB University if you want to learn more. And this is how you would update a counter. You would set it to +1, and it would guarantee that this operation is atomic. User-defined types. Let's go over this quickly. Sorry. So we saw the example before of using maps. Another way to do the same thing would be to define a type, call it geo, and that type would have altitude, latitude, and longitude. And that would also simplify our data model quite a bit. When we define our table here, we would define a position of this type that we just defined called geo, and that would have those three attributes. And you can also do nesting within UDTs, and you can play around with it, but that's way more advanced. I'm running a bit fast because there are concepts that I want to cover. Time to live. Time to live is a super powerful feature that allows us to remove data that is no longer needed. Scylla stores the time to live, or TTL, for each column value. And it's possible to define that, let's skip the poll, that after a certain time to live, the data will be automatically deleted. So it's defined in seconds. And here, for this table, again, we have the pet chip ID, the owner, the time, and the heart rate. We define the partition key as the pet chip ID and time as the clustering key, but we define a default time to live of this many seconds. I don't remember how much that is, but you can calculate it. And what that means is that if a certain row is not updated within that TTL or time to live, after that amount of seconds pass, it will automatically be deleted. And there are more options, but you can see the examples on ScyllaDB University. Maybe a few words about Tombstones before I talk about large partitions and collections. So it might surprise you, or at least some of you, but when we delete data in ScyllaDB and in Apache Cassandra, data is not actually deleted. It's a delete is actually a write, and we mark that data as obsolete. So if I have a pet chip ID with a given heart rate and I want to delete that data, if I perform a delete query, since data is actually immutable, it can't be deleted, it's marked as deleted, okay? And the way that it's actually deleted on this. Thank you. The way that it's actually deleted on disk is done when something called compaction is performed. Let me go to the slide that shows that. Okay, so this is what happens in ScyllaDB and Cassandra when we write data. Data is simply written to something called an SS table, which is a specific structure, data structure. And when we write data, it's written to two places. It's written to a mem table, which resides in memory, and it's written to disk. Once the mem table is full, then say there's a write, another write, another write, another write. The mem table reaches a certain size. It's flushed to the disk as an SS table, and a new mem table is created. Okay, and that means that data is immutable. The commit log is used, as you might guess, it's used for persistence. So since the memory might get deleted if there's a failure, a hardware failure, then if it does get deleted, we would also have the commit log as a backup. But mem tables are written, they're flushed to the disk. And once we have multiple SS tables, let me look for the slide. So mem table is written to the disk. We have multiple SS tables. And once this SS tables, once we reach a certain number of SS tables or a certain size, then we would run something called compaction. And compaction would reduce the number of SS tables into one SS table. Okay, this is the, I can talk just about this for an entire hour. So there are different compaction strategies that we can use. And when we would write data, we can't really delete an SS table. An SS table is never deleted unless we're doing a compaction. So if we want to write, to delete a row, we would simply write to the SS table that piece of row, we would mark it as deleted. And once it gets compacted, a part of the compaction is removing tombstones or obsolete data. Okay, that's important to know. And also when you're creating the data model, that's a bit advanced, but keep in mind how many reads you're doing versus how many writes. ScyllaDB is fast both for reads and writes, but writes are really, really fast because think about it, you just write the data. You don't have to check for any pre-existing data. You don't have to do anything else. You just write the data. It's very fast. Whereas reads can take more time. And that again depends on your data model. And that's correct. I see in the chat window, it's exactly right. For TTL, data is not really deleted. It's marked as a tombstone. And then once compaction happens, it gets deleted. Again, this can have an effect on our performance. Now we're almost out of time, but there are a few more topics that I just want to very briefly present to you, just so you keep them in mind. If you are creating your own data model, it's important to know that they exist. And if you actually need to use them, then you can read more about them. So the first one is materialized views, abbreviated as MV. Materialized views are a way to query not according to the partition key. So I mentioned that we have a table, and when we query the data in that table, we have to provide the partition key. But what happens if we want to query according to a column that's not part of the partition key? In that case, we can create something called a materialized view, which under the hood in ScyllaDB and in Cassandra is actually a copy of that table. But that's under the hood. And for you as a user, once you define the materialized view, you can also query according to other columns. Okay, so that's one thing to keep in mind. Another is creating indexes or secondary indexes. And the concept is similar. It allows you to query according to columns that are not part of the partition key. It's a bit more complicated than that, but I won't get into the details. And maybe the last topic that I want you to remember is something called lightweight transactions. Okay, so that goes together with consistency. I mentioned eventual consistency. By using lightweight transactions, we have an option to perform queries where we can check if a certain condition exists, and only if that condition exists, we can perform the query. Okay, so it's the next level of consistency. It's closer to what you would get in a relational database. And of course, I mentioned the trade-off. So we don't have things that come for free. If we want higher consistency, there are either availability or performance or hardware trade-offs that we have to think about. So those are more advanced topics. Let's see how I'm doing with the time. 5 minutes. So there is a way here, if you have a system running in production and you want to see if you have very large tables, there are different methods here that you can see how to find those large partitions or large rows or large cells. And I put the link here for large partition hunting. So that's how you can debug stuff. So feel free to look at that. And one of the common questions is what's considered a large partition? And that again depends on your use case. Same with hot partitions. There are different tools that allow you to see if some partitions are becoming hot and they're accessed more than others. This is a table of different compaction strategies. I mentioned that the compaction strategy is determined according to the user. There are different options. I won't have time to cover all of that, but you can learn about it on ScyllaDB University. And in 90-something% of the time, the default size-tiered compaction strategy would work for your use case. So unless you're doing something different, then you can probably stick to the default. Before I take some questions, another useful resource is our community forum. I mentioned ScyllaDB is community-based, it's open source. You can check out the code on our GitHub repo. Maybe, I don't know, contribute, send a feature, look at the code for yourself. But if you want to share your use case, ask any question, you can do so on the community forum, and that's forum.scylladb.com. You can say hello in the forum, introduce yourself, also an opportunity to network, but also ask questions. Our engineers and experts hang out there, and also other community members help. So I recommend checking that out. And maybe we have time for a question or two. So there's a question, does the materialized view get updated as the underlying data keeps changing, or does it refresh it constantly? So when we perform a write to the base table, so a materialized view is created based on something we call the base table, and then we can also query the materialized view. When we make updates to the base table, the materialized view automatically gets updated according to the writes to the base table. So as a user, you don't have to worry about updating the materialized view. That happens automatically. Okay, I also added my email here. Feel free to shoot me an email if you have any questions. I'll also send you a message probably by email with some more links and slides. That's it. I hope you enjoyed the session, and I'll try to schedule another one, maybe with more core concepts and ideas for people that don't have that much experience.
Thank you very much, Guy. See you at
Thank you.
the next meetup.
See you. Bye for now.
Bye-bye.